There we go. All right, that should work. Hold on. Wow. Uh, 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 uh. Okay, sound. There we go. Can you hear me now? I was saying all those nice words and everything. Wow. See, that's what I get because occasionally my AirPods will say that they're working in broadcasting and sometimes they don't. I have no idea why. It said they were, so I tried to rely on it. Wow, that was a mistake. Okay, so it seems to be broadcasting now. Um, this is why you need to check your chat. I'm so bad. Okay, okay. I think it's working now. Okay. All right. There we go. There we go. Okay. Um, I was just saying that basically if you exceed the Planck density, I was almost gonna say it was like an error correction. I know Rick has stated it more eloquently in that it's more like error prevention, which is a fantabulous thing because well, otherwise, I think our fabric of reality would have been maybe torn apart or something like that, depending on whose hypothesis you use. But I think we're pretty lucky. So okay, there we go. Duh, duh. Okay, so here we go. Here we go. Okay. Um, so incidentally, let's catch a few folks up because some folks were here earlier. So Rick may enjoy this part. So incidentally, I had a mid-project meeting with Professor Wolfram. I was conjecturing rampantly, and I brought up some things that he hadn't thought about. And to his credit, I got a bunch of I don't knows for certain things, which it's like, oh, I haven't thought about this for a while. Maybe I should think about this again. We went back and forth, and again, there may have been a interesting thing within his system that would slide units around. I conjectured something, but even the words coming out of my mouth, I could tell it wasn't the right analogy. I, it wasn't lined up correctly. Now, I'm not saying some of the things I was highlighting are not important. I have pretty high confidence that they're very important, but Xerxes, one of the organizers of the physics track for the summer school, he gave me some advice. AKA, it was basically within this system, if you actually basically within the graph network, we think of like energy or mass or some sort of transfer as excessive fluxes within the causal edges of space and time. And there are ways to kind of go back and forth. And again, there's still plenty of work for people to find interesting manifold like structures, whatever those may be, to try to capture aspects of reality the best we can, at least for observers like us, which apparently when I'm like, I love that term, observers like us, because it reminds me of like the PBS motto, brought to us by viewers like you, and which apparently he hadn't thought of, and there was much snickering going around, and it was fun. Okay, so basically, I was assigned homework. It was to do additional reading, so I actually did some homework. I did some additional reading, and I'm like, okay, so initially what we had done is okay. So the whole way that I got to this flux thing was I initially conjectured the Planck intensity was something we should look at. There's some interesting things you can do with H bar and C, and we'll save that for another time, so to speak, or well, maybe it is always present. But we for the sake of this, I'm like, all right, Planck intensity, big number. I interpret it as maximal energy flux density. And again, there are some other things you could have here. So basically, it's a measure of energy flux density. All right. So Xerxes was like, well, we need to think about energy. So I'm like, all right, divide out energy. Oh my God, I'm not doing it right. Oh, I need to specify the energy. Otherwise, like, what are you talking about? All right. So I divide the Planck intensity by the Planck energy. Okay. Gives me this number. It's flux. And I remember looking at this. I'm like, to be fair, I think I've seen this before. No idea what it means. I don't have a good interpretation of this. It's just some big number. Okay, inverse length and time. I'm sorry, I had a mark on my computer. I thought it said negative I for a second. I was gonna say, oh, that's got really interesting. Okay. So I look at this number and I'm like, okay, it's literally the dimension of flux. Something about flux is through the causal edge of space and time, and then I'm like, all right, we got all these things here, blah blah blah, and then we got this big psi factor, yeah. So, okay, so basically you have this psi. This is where it gets crazy. This big psi, they basically supposed to have a relationship between these different things. I'm like, okay, all right, that's kind of cool. You go through these. Basically, when you take the square root of that count of quote unquote causal edges or the flux of the system, and you divide by your Planck units, you're gonna basically get out the estimates. However, right now they're estimating that. So, long story short is this was estimated by essentially taking, I think, the Hubble time, dividing it by the Planck time into like elementary steps within the system, and then plugging in that number to help get the number. Okay, hold on. I'll go through in a second, but just to cut to the chase is, long story short is, they have an estimate about 10 to the 116. Okay. So here's the punchline. Hold on, where is the punchline? All right, the punchline is over here. Okay. So if I do the naive thing and literally look at this, and I'm like, okay, I have some homework. Something flux might give us some intuition. Xerxes' comment at lunch was literally, I did this quick calculation. I'm like, flux. What if we do the naive thing? Okay. So long story short, when you do the naive thing, this is what we get. Okay. So if we take that literally as a count of fluxes throughout the graph, hypothetically we should be comparing similar things. I mean, you could just divide it by the units as a cop-out, but if we're literally interpreting whatever this graph structure flux is as something important, okay, I'll treat it as dimensionless. So I take the square root of that, divide that into the Planck length, and we get about 10 to the minus 92 meters, which coincidentally, if we're looking at the initial Wolfram estimates, eerily enough, oh God, why? I'm sorry. I don't know how, there we go, okay. I'm sorry, I'm so ill prepared. Okay. So basically, the elementary length initially estimated was about 10 to the 93. That's 10 to the 92. Elementary time, about 10 to the minus 101. This is about 10 to the minus 100. Elementary energy, about 10 to the minus 30 electron volts. About 10 to the minus 29 electron volts. Note, we did also drop the 8 pi term in front of right here. So we've dropped the numerical factors, and G is the gravitational constant. This is basically the Einstein kappa because it's 8 pi, and big G over C4 is basically just 8 pi divided by the Planck force, or it's the inverse of the Planck force. So coincidentally, and again, this is highly speculative, but it looks like maybe, just maybe, the flux throughout the causal multi-way system within the Wolfram physics project may literally correspond to the Planck dimension of flux. I was not expecting that. Maybe I should have. I look at this result and I'm like, how did he know? He did a quick Q&A the other day, and I had followed up after, and I asked him if I could show him something crazy. He's like, oh, sure. And he's going over, and I show him this provisional definition. And he turns to me and he's like, no, no, no. I am of the opinion now that this must be the way it is. And I'm like, I tend to agree with you. Here's why. I got to, that's interesting. He was thinking about it, but he had to go to dinner. So, yeah, maybe something for future work. But I'm like, oh my God. Because these things are derived differently. It's like, this is about time of universe. This is just a Planckian boundary. Then again, age of universe might actually be a Planckian boundary. So, I mean, maybe we should expect this, but I'm just like, huh. It's also one of those things, if you happen to get a result and you're coming at it from more of a philosophical, kind of like Professor Barron's has said that, listen, hey, if anything comes out of some of this individual stochastic stuff I'm doing, he's like, I am a philosopher. He's like, physicists, of course, will introduce me as a physicist, which he is a physicist, but he's like, no, no, I'm a philosopher first, so I can respect that. But yes. So I'm sorry. Oh, hey Natalie. Yes. I am. I'm quite a bear, I guess. Okay. Let's see. Where are we? Yes. We finally have audio. Have I watched The Preacher? No, not yet. The Doomsday Preacher. See, I was waiting for Y2K. I kind of fizzled out. I was waiting for 2012. 2012 was actually a pretty good movie. I don't know. We still seem to be here. I don't know. I think the biggest threat to ourselves is probably ourselves, but maybe that's just a recursive thing. Personal opinion there. Well, see, here's the thing, Bill. As far as the edge of the system has a limited size. Now, perhaps it would iterate forever. Perhaps it will have just go on forever and then disperse following other models, because that's the interesting thing, because within this model it's like, I don't know, do we have many worlds? Are we constantly going to be splitting? Is everything just going to adjust in a certain proportion that we wouldn't even notice? I don't know, but the thing is, if this is the constant of proportionality, or at least within this model, that's what I'm hypothesizing. The thing is, if this number actually does grow, it's literally going to adjust these units. So that means if you're going to add additional size to the system, then if this gets bigger and you have the Planck length there, that's a really small thing already, and you're going to keep on dividing it by a larger and larger number, it's going to get smaller and smaller. However, perhaps if literally the only reason I was able to calculate any of this is just because I have a target to look for. I'm basically just kind of using what Thad taught me about, you have some target, unleash the Wolfram language and Wolfram alpha to just try to compute it, be a numerologist, nomologist. Somebody else smart said the term nomologist or whatever it was the other day. I'd first heard it through Rick. Where are we? But like, if this was a constant of proportionality, maybe there is stuff underneath that we can't keep track of because it's just so ginormous. But if it's a Planck unit, and the Planck units were to, literally, this might actually solve that problem. I may be making a massive error here, but if we could root and ground the Wolfram Physics Project into something where, well, most people are going to agree, because remember, all good physicists, it's h bar equal to 1. Hence, aka Planck units, are set equal to 1. What, are you going to argue with a 1? Again, there might be lots of other reasons, but I don't know. Oh, God, no! Don't get me... The crazy thing is, my idea before this, Rick, I've been trying to find something before I did this calculation. How could we try to estimate the single energy contribution from a single causal age? I had no idea. one of my mentors kind of gave me an idea, and I'm like, wait a second. What's something that we potentially have calculated? Pretty sure Jonathan's simulates some minimal black hole mergers and stuff. I'm like, okay, if we can literally model a minimal black hole, we know at least generally what we think the parameterization of that would be. It'd be the Planck mass or Planck energy within a volume. So basically, a maximal mass energy divided by a minimal volume within the standard SI units. Okay. If we could model that, and apparently they have seen things that literally seem to break off from the causal graph, or maybe it's attached by like a single thread or something like that weird. I mean, the interpretation, well, it seems to be breaking off from everything else, so to speak. It's there, but it seems to be disconnected. That kind of sounds like a black hole action. So I'm like, all right, if we could do a minimum thing, and we know the parameterization of what we would need, if we count the edges, we should be able to divide that into the Planck energy or Planck mass, and then get the contribution from an individual causal edge. Now, we may have kind of simulated them, but the level of graininess you would need, especially if you're trying to do an elementary thing that's like 10 to the minus 100-ish, I don't know if we have enough compute in the world. I don't know if we have enough compute in the probably solar system, but I don't know if we can do it right now, long story short. So, but if there is a Planckian limit, that may put things on some basis that might be harder to ignore. Now, is that the full story? There's still so much to be figured out and everything. Like, what the heck is gravity and everything? Because gravity's always that pesky nuisance that seems to be popping up, and it's a force. It's not a force. No, but it is. But it isn't. So maybe somebody watching now or temporally in the future will figure it out. Okay. Any tips to find out if it's there? Dirac's large number. I mean, I just call it the really large number hypothesis. It just, I'm a simple dude in some ways. I'm just like, all right. And I also got to thinking, I'm like, well, that has an equation. It's like, you got a thing, you got 1 over a thing, and you get a volumetric thing divided by a circle. I'm like, okay. And to be fair, if we're going to conjecture, it's like, all right, the minimum length, the maximal length will just be in the same units, extended beyond that. Okay, maybe. But then again, you have to deal with other units and their inverses and say that they're doing things. So, I don't know, that kind of, again, a lot more to do. I'm not saying I have the answer. But, Phobos, the really large number hypothesis is something like this. I'm sorry, I'm distracting myself. Don't mind my arbitrary calculations trying to hypothesize that the CMB or whatever that might be is actually, universe's operating temperature would actually be Euler's number. That wouldn't that be at all. Let's face universe temp E. Oh god. Okay. What was? Really large number hypothesis is okay. So you get the Planck length. Planck length is really small. All right. Redonkulously small, like 10 to the minus 35 meters. All right. You do 1 over that, you're gonna get a really big number. Well, that's in the wrong unit. Do literally the naive thing. What block would I need to put here to get the right answer? Meters squared. Oh look. That's about 10 to the 8-ish, so about 100 million times larger than the diameter of the observable universe, or radius, because it would go up larger. I can do that calculation. You get a lot of really interesting numbers. That's why I kind of got overly excited when I looked at this. I'm like, this seems to match a lot of the derived units extraordinarily well. Why? Maybe when Thad was elaborating on what the heck is one what? That was a very impactful conversation because literally I had to throw out a prior from about an hour before. I'm like, okay, all right, I'm listening. I'm like, okay, I can interpret that way. Um, where are we? I'm sorry. I'm jumping all around. Let's see. Why is my shirt on? I am currently in a university. The AC also did kick on a little bit more. Maybe we'll go there. Da, da. Let's see. Okay. No computer is faster than nature. Yeah. No, I mean it seems that way. I mean, if you're gonna run something at a maximum frequency, I mean, nature would make a lot of sense. So, okay, let's go. Okay, I should probably actually get into actual calculations because I do need to finish this project. Okay, where were we going? Okay, so that was how we got here. So, all right. So our energy, so if we do flux and then we multiply it by the unit energy, and see, the confusing thing is like when you listen to Professor Wolfram, a lot of times he'll be like, well, we notions of the elementary energy. Okay, h bar, elementary unit of action, really small. Planck time, Planck length, elementary units there. Speed of light, really fast, like really. Okay, now you could say that's an elementary speed. To an observer like us, it seems ridiculously fast. Just kind of like a Planck energy. It's like it's about the energy in a lightning bolt. It's like I've touched two switches that were not together, and I completed the circuit when I was a young lad and zapped myself twice because I turned the lights on and then I'm like, why did I turn those on? I turned them off. Sometimes it takes me like 3 times to learn. But yeah, so like as an elementary unit, it's like yeah, but we've also defined our units in a very particular way. So that's why I think there was a live stream like a month or so ago. It's like I was trying to figure this out live because like you say things and it's like, is that really true? It's like okay, to an approximation, I can kind of say this, but a good analogy, something laid out in basically, for lack of a better term, an ironclad, I don't know, maybe neutronium clad, whatever you want to say, statement that it's like, this, to my knowledge, is basically as true as I can get this statement. And the best thing I can get for like the Planck units and these boundary units is they are the basis. They are the basis of reality, of which the rest of all the other stuff and things come about. How exactly that is, I don't know. I I ain't God. So I don't have that answer. Okay. So we went through our calculations here. It's the inverse blank force, therefore natural language. Okay, so basically that gives us the Planck force because so energy, yes, okay, so elementary energy. Wait a second. This, huh. I mean, it should be that way, but why does that make sense? Okay. So an elementary. Oh, because we're dividing. Okay, so if we were to do something else then, because this is going to come out to be the Planck force. Okay, maybe it's not. What did I do? Okay, no, it is the Planck force. Okay. I'm getting, 1.334. What? Fundamental black hole constants? I've never seen that before. Konichi, what? Okay. Izod energy loss for fitness. That sounds like a Superman term. Okay. Fundamental black hole constants. I've never seen this term. Why? Black hole. Hold on. Parameters of the properties of mass. Okay. These parameters, along with the fine structure constant. Of course! Oh, what's the general AI thing you say? I'm like, okay, yeah. Found to be constant even near supermassive black holes, providing I'm very dubious on that. Okay, I remember some of these studies. Hold on. But as far as force goes, what the heck is that? Okay. So 4/3. Okay, so it. Yeah. Okay. Three-dimensional sphere. That's what I'm hearing. I mean, I don't know, that is also interesting if you have some lattice or something like that. I mean, do a 2. See if we can extend our data with extra stuff. Okay, that's interesting because you could rewrite that as 8 over 18 log 3, 2, which, okay, 8 is associated at least within Dad's model is mass, 18 is charge. Okay, that might actually make sense. It also has all the numbers. Yep. Save this guy for later. Oh, God. I'm gonna be dead and gone. There are gonna be bajillions of screenshots of this and plenty of inappropriate things that, yeah. Well, maybe hopefully they'll just get lost to history. Like, this is literally what I do. It's like, all right, extra information, do a 2, do a 5, do an 8. See if there's an interesting closed form. This has literally been thousands and thousands of Wolfram holes. And, yeah, I ain't as fast as that at doing these things, so ultimately it's like, he wants to piece together all those things. That's fine, and I kind of just got a little bit lost, and I'm like, let me look at things that hasn't looked at. Just kind of doing the same thing. Okay. So I should not spend time on this. Okay, I'm sorry. I'm gonna sidetrack down another Wolfram hole. Oh, well, Rick is right. To a galaxy, light is pretty slow. See, it's pretty slow. Morgan is saying that the Earth is a black hole, and the core of the Earth is the sun. The Earth orbits the sun, and Jupiter is a failed sun. As 3 suns slowly falling into black hole Earth, won't you come? And then it occasionally rains. All right. So, pulled inside out. I mean, I don't know about that. I wasn't there for it, but who knows? Oh. It's okay. It's okay. The chest here is still here for now. Okay. All right, let's continue onward. Okay, so what do we need to do? Okay. Let's get our notebooks going. All right. I have a very bad habit of getting distracted. Okay. Okay, so we were just going through this here. We were going first derivative are dimension 1, dimension 2, dimension 3. Seems to line up there. Okay. So. Okay. It's determined by the actual evolution of the multi-way system for the particular rule with whatever foliation or other features define the way we describe our experiences in the universe. As a simple motto, we might then characterize what we observe as being generational states. Let's go over here. It's discussed here. General evolution. Okay. Systems like cellular automata always update every element at every step in their evolution, but in a string substitution system, as well as in our hypergraph-based models, The presence of overlaps between possible updating events typically means there is no single consistent way of doing this kind of parallel updating. Nevertheless, in studying our models in earlier sections, we often use steps of evolution in which we updated as many elements as we consistently could. As we could also apply this kind of generation-based updating to string substitution rules. Okay, so the rule, we got this thing. And one state is produced from another by a single updating event corresponding to a single application of the transformations in the rule. Okay, so we start getting some complexity there. But we could also consider producing a generational multi-way graph. And I do also appreciate the amount of quotes of stuff. It's like, yeah, here's the general concept we're laying out. We're going to explore the territory. And it's like, at least Professor Wolfram's seen enough that this is what he likes looking at. He tries to find out cool things. He literally has 6 hour just videos of him like on like a Sunday just going through, trying different things. And so he is a beast. Okay, so, but the results is now radically simplified through this because the increasing number of update events, this is rendering for the evolution. Okay. All states attained at generational steps do appear somewhat in the full multi-way graph, but the full graph also contains many additional states that, among other things, can be thought of as representing all possible intermediate stages of generational. Oh. So it almost sounds like that hypothetically, if you were to have a graph you could construct or some network of stuff doing things, so to speak, if you had that, while an observer like us might not have all this information, it sounds like there may be things that can happen that don't necessarily happen, but in order for us to make sense of it, we need to parse it or try to exploit. It kind of reminds me of Professor Barondus's lecture on Wednesday. The big thing that Professor Wolfram had said was, okay, from what I understood, he's like, all right, so now you're just front-loading the thing. Because I think one of the issues that people run into with like quantum mechanics and stuff is, okay, we have these kind of crazy things. How do we post-justify them? It's like, okay, well, there's obviously dual coherence. There's a measurement problem here. There's spooky action at distance, entanglement, whatever you want to call it there. It's like, okay. So we try to explain those things. From what I take away from Professor Barondus, he's like, all right, hypothetically, if we could take the non-Markovian dynamics rather than just taking a slice and then just saying that we have this slice and then we can figure out everything else. And then we kind of run into some of those problems. He's like, all right, if we had the entire causal history of the universe, then the problems we run into actually wouldn't be there because we would have been able to keep track of all these processes, and quantum mechanics kind of loses its mysterious flair. And it's kind of looking like just a standard classical probabilistic modeling, or at least within the model. Not to say that it's just probability based. Hey, who knows? I don't know. If there's free will, cool. If not, hey, destiny it is then, I guess. All right. This contains initial states, among other things, to be thought of representing all possible intermediates. Okay, so it kind of sounds like the Feynman path interval. We're just kind of estimating over infinity. The infinities might not actually be there, but we're hoping everything is going to cancel out and things will make sense. Okay, the generational step, possible trajectory. Okay, if not, the case of the generational micrograph involves just a single path. Consider the rule. Okay, the general micrograph is now. Ooh, loops. The generational multi-way graph is in a sense a compression of the full multi-way graph, and one way to think of as being derived from the full multi-way graph by combining sequences of edges when they correspond to updating events that do not overlap on the string. There's also another view of generational evolution considered the branchial graph from the full multi-way graph above, This branchial graph is derived from the layered foliation that we have here. All right. The branch poles in this graph, shown as adjacent nodes, can be thought of being two kinds. The first are produced by applying different rules to a single part. Okay, ABA to ABBA and BBA in the second hand. Okay, in the full multi-way graph, no distinction is made between these conjoined branches. Blah blah blah. Maturing west strings in the second kind of branch pairs can be combined. Indeed, this provides another way to construct a generational multi-way system. Look at branchial graphs and take a pair of strings corresponding to spatially disjoint updating events, and then net these together to form generational steps. If there's only one way to do this for each branchial graph, one will get a single path of generational evolution. But if there are multiple ways, then the generational multi-way graph will be more complicated. Okay. Let's see. Determined by the foliations. Given a foliation, one can assemble strings corresponding to generational steps using the procedure above. There's always an alternative, however. Instead of combining strings from a branchial graph to provide the state for a generational step, one can always, in a sense, just wait. And eventually, the full multi-way system will have done the necessary sequence of updates to produce the complete state for the generational step. Whenever there are no possible overlaps in the application rules, the generational multi-way graph must always yield a single path of history. Okay? But there's also another feature of such rules. They are guaranteed to be causal invariant. There are, however, plenty of rules that are causal invariant even though they allow overlaps, in a sense because their right-hand sides also appropriately agree, and for such rules, the generational multi-way graph may have multiple paths of history. Okay? Okay. The generational multi-way graph, because it ends up having the same output. Wait, is it the exact same? A to A to... Okay, so it's the same. Starting from A, however, the rule yields the full multi-way graph. Generational multi-way graph. Okay, in an alternate ring, these graphs more steps repeatedly. Note that in case the number of states reach t after grow like t squared. Oh god, that's very... I'm sorry. I see things that I like. 1/2 t squared plus 1. Okay, in the second case, okay, I'm seeing things that... I'm not going to pretend like I know exactly what's happening there, but... I'm seeing forms of things that occasionally... kind of makes sense to me. All right, let's see. Fibonacci, cool stuff. All right, All right, so we're just going to go back now. Yeah. So, let me see. Where are we at? Give me just... Oh, hold on. I need to... Oh, God, we've been playing for 40 minutes. Let me play my little warning.
World exists on the top of a giant turtle.
Okay, that was not the warning I was looking for, but they have a little section at the summer school for Stephen quotes. I included some turtle stuff. All right. No, where is it? Over here. God! Where's the... Okay, all right. We're going to conjecture ahead. Hold on. Here we go.
Although this is going to be weird, and it's going to be about a different...
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one ruliad. I don't think it rules them all. And it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulial turtles. Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Okay, so coincidentally, one of my friends, I was helping her with her philosophy homework a few years ago, and one of the things was like reading like, I don't know, like a 60-page essay by like Thomas Quine. It's like, I'm very ADD. How about this? Here's a 40-minute interview with like Thomas Quine himself on Quine's 2 dogmas. Let's listen to this. Go over some stuff. I think she got an A. somebody asked me the very next day. They were going over something about Quine, and I just literally just gave the generic response that one would give, like if you had literally just watched Quine. Somebody was like, "Oh, you must spend a good amount of time studying philosophy and all these things." I'm like, "No, I literally just listened to a YouTube video last night." So, so, dude, Professor Barndas is crazy. He gave literally a 4-hour lecture and ended up going to about 5 unofficially and stuff. We went for so long, the HVAC system shut off at 10 o'clock. And at 11 o'clock, the AV stuff that was hosting the Zoom also kind of conked out. And we stuck around for almost another hour, still chatting and stuff, asking questions. And Professor Wolfram seems to have a good dynamic. Apparently, Professor Wolfram was not necessarily aware of all the things that Professor Barondus has been up to, and I think it would be kind of cool to see them on either a live stream or a podcast together, because I think there's some overlap. That's an opinion. Did I find all the answers I need? No, I'm still searching for many answers, but I think that just requires me doing them. Okay. Some K new states where K is related to num2 elements produced by a single updating event. But K is around 1-ish, I think. And a generation of evolution, therefore, the total number of states. Oh my god. In a multi-way system will be multiplied by a factor K. Okay, but to relate these to observed quantities, we must ask what time an observer would perceive has elapsed in one generational step of evolution. From our discussion above, we expect the typical time an observer will be to coherently maintained impression of a definite classical-like state will be roughly the elementary time multiplied by the number of nodes in the branch-like hypersurface. Okay. The number of nodes will change as the multi-wave graph goes, but in the current universe, we have it defined to be big psi. Okay. I mean, this raises all types of questions here. I mean, it's like, all right. So that gets into, it's like, is universe expanding? Was it expanding? Is it still expanding? Is it at some maximal state right now? Are we collapsing back down? What's going on? So I don't have all these answers. I could speculate rampantly, but it's trying to stay grounded to something at least that I could justify by some philosophical arguments, so to speak. Big psi. Okay, so we have the equation. Oh, so it's elementary time. Okay, so let's just do this real quick. I'm just curious. So we don't need that. We don't need that. Okay. So we take the. Okay, just take this number. Take this flux number, and we're gonna set this flux number equal to. Just gonna be a savage and rip the dimensions out. Okay, so I got that big number there. We're gonna set that equal to x, which is our k. We're gonna raise that to. Okay, let's just grab the Hubble time. Hubble time unit. Okay, so let's do this. Let's do 13.78 billion years. Okay, we got a bunch of seconds. It's the unit we want. All right, so we're gonna take this ginormous number, seconds. We're gonna divide it by. We're gonna have our capital psi again. I'm gonna put this in the denominator, followed by our elementary time, which should have right here. Okay. just going to pull this out. Come on. All right. So let me just make sure this is right. Okay. So Hubble time. We got our time thingy up there. We got that thing that we're plugging in there. Okay. Now we just put in our elementary time thingy. Oh God, we don't need all those quotations. Okay. Finish that. Enter. Okay, so yeah, so this is a giant. Okay, so let's calculate that part first. Okay. Okay, so it's giving us some factor. Double time. Time drift. Oh. So that means I need to play time warp. Don't mind me. Okay. I'm sorry. I love this stuff. I also live for irony. Okay, so that's the number that we're getting. All right, so get that number there. So that's this thingy here, so 3250. Okay. So, at least according to this, okay, so we get positive and negative answer, so that's interesting. I mean, we got it squared. Oh, it's to that power, that's why. All right. So what is this number? Huh. That's... I thought... If there wasn't a pi there, that would be... Well, then again... Okay, I think I looked... I think this is actually in some of Thad's equations. Okay, so we made an assumption. So the last digit or so is probably... Just take a quick look around. 7 times 3 tetrahedral volumes divided by 2. Oh, excuse me, mean Cuban tetrahedron volume. Again, this is... I probably have thousands of these things that are absolutely nothing. Just cute little forms that I try to occasionally remind myself of. So over -1, alright. So we're gonna have to go a little bit deeper. Yeah, these last digits are very sus. Let's do this. Could always be 1. Let's check this. Let's do our standard spread numbers. Do pentagonal. Okay. I mean, if it was just log 64, I mean, that would be, it's like, oh, wait. Logs? Logs are very useful. Let's see a lot of the same friends that pop up again and again. It's constant. Okay, so I don't really have anything. Yeah, can't. Realistically, we probably only have a couple of digits of accuracy, so yeah. I don't think we have enough information unless we would back propagate it, but okay. I don't have time for all that. Yeah. Okay, I need to stop the rampant speculation that I'm doing. Yeah, just to jump to the left, just to jump to the right. Oh, no. We're actually, the Wolfram Summer School's in Waltham, Massachusetts. Professor Barondess is over at Harvard, so he literally just drove over. No, he was here live. He's a fascinating guy. He's so full of history. I mean, just the interaction between Professors Baroness and Wolfram were just... It was great because they would be... Well, to be fair, here's the deep lore for this, here's the deep lore for this, and they're very knowledgeable on history. Yeah. Well, see, that's the thing. How are we interpreting it? And again, I understand why. It's like, all right, we just assume sphere stuff. We assume spherical thing until we have a reason to assume otherwise. Looks like stuff is going away. Yeah, maybe it's just spreading out. I don't know. All right. This platform does not have the X-Files clip. Welcome back, Dan. It's, no, yeah, hopefully in the future, I don't know this, I just think it would be cool if maybe somebody happened to host Professor Baroness and Wolfram. I think it would be an interesting chat. So, all right. So I managed to, don't mind Rob Zombie in my ear. Okay, so I managed to not do all the things that I wanted. Okay. So, substituting previous result for T. Okay. So that's the elementary time, but did they go through how they derived that? The elementary time is, okay, divided by that, but we're using that to derive that. Yeah, I feel like maybe this should be explained in a slightly different way. Just because we're using that elementary time, but that needs to be calculated by other things there. All right. Yeah, so if you just keep on splitting and everything is just going to double and everything like that, then we're all doubling together. Okay. How much curvature? Geometry time, depending on the speed of light, but... Okay. It's... Okay. Hold on. Where is it actually defined? Because I remember going through this. Okay, here we go. Okay. That's where it is. Okay. But we still have that in there. It's just that the Hubble time divided by the Planck time. If we just do that, we get 0.377 times 10 to the 10 Gregorian years. Okay. So let's do this. Let's put that in. All right. That's what we want. All right. No, some of these things are not quite lined up. Okay. So I got that. Let's divide that by the Planck time. Divide by Planck time. About 10 to the 61-ish. Yep. Okay, so we get that number there. It's just they still have this factor here. That's... Yeah, it's the thing that... For example, K is less than or equal to 2 lua, and limit of K is related to the efficiency of causal invariance in the underlying rule. Okay. Get solve for E to get... Wait a second. Oh my god! Logs are useful! Okay, Okay, so k needs to be greater than 1, given the transcendental equation. Okay. 61, square root of k, okay. W is the product log function that solves for W, logged in, okay. But for large, log k, we imagine that would be okay. Okay, so they're running the log for it and trying to see what it makes sense. Okay. So that's where they get about the 10 to the 116. Okay, so I mean it's in the ballpark. They went for extremely close to but even for okay, we were at 10 to the 12. Okay, 115. Okay. You have to know the underlying rules and the statistics of the multi-way system it generates, but particularly at the level of the estimates we are giving, the results are quite insensitive to the value of k, and we will assume simply that k is about 10 to the 116. Okay, so in other words, the universe today, that's how we get... okay, all right. Number of elements in an electron. Okay, so we're basically just taking the square, the third of the sixth root. That's kind of cool. Must be less than about 10 to the minus 22. Nearly 10 to the 60 times our estimate. Okay. Electrons. Our experiments 10 to the minus 22 meters. What? Why is I mean, are they squaring that? Are they cubing that? It's oh, number of elements in an electron. Oh, look. Wait. For some reason that kind of looks wrong. I'm sure I'm incorrect, but the total the spatial hypergraph is estimated to be 10 to the 200 times the number of elements of all known particles of matter in the universe, suggesting the sense most of the computational effort is spent on creation of space rather than on the dynamics of matter as we know it. The structure of moles implies not only in length and time, but also energy mass must ultimately be quantized, as it indicates the mass of electrons about 10 to the 36 times smaller than the quantized unit of mass. 10 is greater than 10 to the 36 times the quantized mass. Okay, far too large to expect to see numerological relations between mass particles. Well, localized structures, there's no reason to think the structure much smaller than the electron might not exist, corresponding to particles with masses smaller than the electron. Such oligon particles involving comparatively few hypergraphs elements could have masses that are fairly small, multiples of 10 to the minus third elementary energy. Suspect their cross sections for interaction will be extremely small, causing them to drop out of thermal equilibrium very early in the early universe, potentially leading to large numbers of cold relic oligons in the current universe, making it possible oligons could play a role in dark matter. Relic oligons would have more or less perfect ideal gas. Current data indicates that only particles constituting dark matter probably have masses of greater than 10 to the minus 22 electron volts. I mean, good luck detecting that, if that's even a thing. Okay. As we discussed in the previous section, the structure of our models, specifically the multi-way Coulomb graph, indicates that just as the speed of light c determines the maximum space-like speed, or the maximum rate which the observer could sample new paths of the spatial hypergraph, there should still be a maximum branch-like speed that we shall call zeta. In terms of maximum rate which an observer can sample new parts of the branch graph, will affect the maximum speed at which the observer can become entangled with new quantum degrees of freedom or new quantum information. Based on our estimates above, we now give the estimate for the maximum entangled speed. We could quote it in terms of the rate of sampling quantum states or branches of the multi-way system, 1 over the elementary time. So that's going to give us What do we have for our elementary time? It's over here. Nope. Put it over. Where is it? Just grab this guy. And over. Seconds. Oh, that's kind of interesting. I mean, that's pretty close to like 10 to the 100 hertz there. That's kind of cool. Why does this number look so familiar? Is that the, hold on. Mean displacement law. Where was it? I think it's 4.96 is the thingy. Okay, yeah. It's 4.965. Where is it? It's, I don't know. I just have these numbers like stuck in my head for a couple of digits. Okay, hold on. Where is it? It's something about like the log of 5 or something. Okay. Maximum wavelength is 4.965. Okay. Wow. That's got a lot of digits there. All right. 4. I mean, I have no idea what this is. Yeah, I got nothing. Nope, nothing. By connecting to these early features, best in terms of the energy associated with it, hypergraph, in which case the result based on our estimate is... Okay, so it seems to come out to be the Planck power, because that's about 10 to the 52 watts. There to quote towards the energy. Okay, so let's take this. Let's take our elementary energy we have here. All right. Okay, so elementary energy, electron volts. Okay, elementary energy. We're going to divide that by the elementary time. And I mean, that's going to give us power. I mean, that's energy divided by time is power, so... Wow. I wonder... Did people realize this? Because, again, the only reason I know this stuff is Thad, like, drilled it into my head. I'm just like, he stressed the importance. I'm just... Again, it's like, oh, how does somebody know this? It's like, no, I've literally gone through it. It's, meters... Okay, so energy. Oh, excuse me. Divide by time. Derp. It's 1 Planck power. It literally is 1 Planck power. What? We can give the estimate for maximum entanglement speed. Okay, but in connecting it to observable features of the universe, it seems better to quote in terms of the energy. Hold on. What are we even talking about here? Such oligons. Multi-weight, indicate speed of light. Okay, now sample. Okay. Which an observer, how we even define observer could sample new. There should also be a maximum branch-like speed that we should call zeta. During maximum which observer can sample new parts of the branch won't affect the maximum speed which the observer can become a tank. Ah, so it doesn't need to be an observer like us. It's kind of like taking what Bill was saying. Okay. Based on our estimates, we can now give the estimate for the maximum entanglement speed. Quote in terms of sampling or quantum branches in the multi-way system. Okay. In terms of observable features of the universe, it seems better to quote in terms of the energy associated with edges of the causal graph, which in this case are estimates. Okay. So let's just do another quick thing. Okay, so the elementary energy they estimate is about 10 to the minus 30 electron volts. All right, and then we'll divide that by elementary times about 10 to the minus 101. Minus 101 seconds. General relativity maximal powers. Okay. I mean, again, it's within magnitude. Okay, yeah, because they don't have any more numerical factors there. I mean, maybe I don't think we should be surprised. Hypothetically, if the flux density throughout our realm system, you want to model it in a particular multi-way system, imagine my shock. The flux is literally the limit of Planckian flux. And it appears, again, could be just completely a coincidence, but if we take that number, imagine my shock if you take the elementary energy, divide by the elementary time, and we basically get the Planck power. Now, hold on. In terms of energy associated with a causal graph, okay, so it would be, that's the Planck energy per second. The Planck energy per second is Planck power. This seems large compared to typical astronautical, but one could imagine being relevant. For example, oh my God, okay. So we got the Planck flux, and we got the Planck power. That's not too shabby. Okay. Somebody's throwing an intergalactic kegger. Yeah, there was there's some of the high school kids there. And to be fair, I'm not sure what bill it is. I don't know what that is. Oh, thank you. All right, let's see. Oh, okay. No, okay. Crypto is it's working on the manufacturing and everything. This is the thing. It's like I'm mostly theoretical right now. If we were to build something, I think the ultimate goal is one. If we can literally just take nitrogen out of the air and just transform it into water, that would be really cool. Now, in order to get there, or even the first step of universal replication, you would need literally, we're basically going to need fusion level power, which is also probably going to require superconductivity. Long story short, I think the path is achieve room temperature superconducting, have sustainable, scalable fusion, figure out what's going on. There we go. Profit / true post scarcity. And if people will still want to fight, they can get in the ring. There we go. Let me see. Oh no. It's okay. I'm a very dangerous person. Oh no. Oh, the debauchery. It's okay. All right. Okay. I would like to see that. Hey man, I spent a bunch of time in Utah, and apparently they had discovered cold fusion, but then something not being able to replicate. I mean, I don't know, man. I've heard interesting things on some of the APEC talks and everything. I've heard folks talking about it's like we can break the water bonds and then recombine the hydrogen and oxygen and get out like an impressive magnitudes of power. I'm like, that's cool. Maybe it's classified. I don't know. But if we could do that, I mean, that's a game changer right there. So, okay, maybe that's what you're talking about. All right. Oh, God. It was so pretty. Man, come on, man. Nobody would ever keep things quiet. It's not like I was watching the ICTS, which is basically India's Institute for Advanced Study, listening to an experimentalist one night. He's like, yeah, so we did the experiment in a particular way, and within this particular frequency range, all of a sudden we saw a jump in 20 magnitude, or like 20x improvement in output for that small range. He's like, we don't know why we were able to do this, and I went back the next day, and the video wasn't there. It's I'm sure they were just taking it down for reprocessing and everything. That's the thing. See, this is what gets me excited right now. Yes, we can. I agree. I agree. It's just, again, my MO is I don't have the answers. There's a lot more smart people out there than myself. Maybe I should reach out, talk to them. Will I always learn something that's extremely useful? Not always, but very often I learn things that are maybe not right then, but at some point it just kind of reveals itself, and it's like, oh my God, how did they know? Kind of like it happens with Professor Wolfram sometimes. It's like, I have no idea how this guy has his intuition. It just kind of works. But it's okay. They're not that shy. But okay, so let's do this. Let's add some calculations with derived units. Okay, so now we need to get to, oh God, how do I have this? The zeta? Okay, so let's put zeta in here. We can insert. Oh my God. Where is it? Symbols. There we go. Special character. Where is our zeta? There we go, zeta. Helps if I actually put something there. All right. All right. Oh God, I'm gonna have to organize this thing. I'm so scatterbrained. I don't know if anybody's ever read the mixed up files of Miss Basil E. Frankwilder. I feel like her sometimes. Okay. In regards to zeta, in regards to the maximal entanglement speed, zeta notated, because we're doing notation. Notated by zeta we may express this as 1 over, okay, I need to have, do we have t-bar? Even old enough to show, I'm sorry, I got some Weird Al in my ear. What was I just doing? Special character. Do we have a t-bar thingy? Capital T. Oh, capital T. Okay, it's the same thing. Okay, I'm just going to steal it from here. Where was our elementary time? Time! No, I don't want that thing even. Although it'll probably give me the. I literally just want it. Just. Here we go. No! Oh no. Okay. It's not gonna paste. Okay, so I just need to. We got this. Just put the code in here. There we go. All right. I feel like I should put that in the code output. There we go. Okay, so then I can just set variables and calculate away. All right. So that's what I should do. Okay. I'm gonna take a quick smoke break, and I should be back. I think they're still open till 11 here. I could be wrong. I might have to go back to the dorms. Let me file. Save as. Wolfram Flux. All right, file. Save as. Wolfram Flux. What do we do? 7, 5, 25. This is 1. Save to cloud. Croaking. The battle droids were broken. The thread I admire. I can't sing the song. I met up with Darth Maul and now he's toast. I'm still here and he's the ghost. Guess I'll train this boy. That sounded very wrong out of context. I'm just constantly publishing Wolfram Flux. Okay. All right. So we may have found another plank unit for the Wolfram model's maximum entanglement speed. I mean, it's pretty close right there. I mean, I don't know. I was looking for a method. I mean, I was not expecting this. God. I'm not going to sleep on like Tuesday night, am I? I'm going to be up all night finishing this. I know I am. It happens. All right, so I am going to take a short smoke break, and we should recommiserate in a little bit. All right. All right. To be fair, Morgan, I literally gave it a screenshot of something that I wanted to do. I even used the Wolfram Notebook Assistant. It gave me butt tons of errors. Then again, I should probably just spend the time and actually just work with the code myself, because at least try. So other than that, I'll catch you guys in a little bit, and other than that, take care, my friends. Peace out, everybody.